Hello everyone and welcome to the second session of our three-part Applied Remote Sensing Training, SAR for detecting and monitoring floods, sea ice, and subsidence from groundwater extraction. My name is Erika Podest and I'm a research scientist at NASA's Jet Propulsion Laboratory, as well as an instructor with the ARSET program. I'll be hosting today's training and the rest of this webinar series. Today, I'll be joined by Dr. Erika Fielding, who's a research scientist at NASA's Jet Propulsion Laboratory. He'll be focusing on measuring surface subsidence due to groundwater extraction using InSAR. To begin, I'll provide an overview of our training before we begin this session. I'll first be providing an overview of our training before we begin this session. The objective of this webinar series is for participants to learn how to use SAR to detect and address potential disasters related to sea ice, floods, and groundwater extraction. And these sorts of events can have a large impact on human lives, infrastructure, and the economy. So SAR can be critical in informing on-the-ground efforts on disaster mitigation efforts and resilience. And by the end of this webinar series, participants will be able to generate subsidence maps due to groundwater extraction in order to inform risk and resource management, detect and monitor sea ice to identify potential risks to shipping and coastal erosion. So that was the first session. And then the last session, which will be tomorrow, Wednesday, November 1st, will be to detect and monitor floods in order to more closely monitor increase or decrease of floodwaters and better inform disaster response and management. And here we can see an outline of this webinar series. Today is the second session of this three-part series. All presentation slides, recordings, and Q&A transcripts are available or will be available on the training page. There will be one homework assignment, which will open on the date of the final session. That will be tomorrow, Wednesday, November 1st. And that homework assignment will remain open until November 17. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. And finally, before we get started, I just wanted to remind everyone that if you have a question, to please type it in the questions box. And under this platform, it is located in a different place. It's at the bottom right under the 3 points. There's a drop-down menu. And one of those three options in the drop-down menu is questions. So please write your questions there, and we will address all questions at the end of the webinar. And feel free to type in your questions as we go along. All the questions will be assembled into a Google Doc, and that Google Doc will then be posted onto the training page with all the answers. We're very excited to have Dr. Erika Fielding as guest lecturer today. He has taught several other ARSET trainings on the use of InSAR for looking at earthquakes and landslides. Today, he'll be introducing a brand new topic, which is the use of InSAR to measure subsidence due to groundwater extraction. Thank you so much, Dr. Fielding, for joining us today and for so generously sharing your knowledge and wide experience in the use of InSAR, in this case for groundwater applications. Welcome.
Hello, I'm going to be talking about subsidence due to groundwater extraction. My name is Erika Fielding at the Jet Propulsion Laboratory, California Institute of Technology, a NASA laboratory. And a number of the slides today were prepared by Zhen Liu, who also works with me here at Jet Propulsion Laboratory. So this is part of the series of webinars on using SAR for detecting, monitoring floods, sea ice, and subsidence due to groundwater extraction This is session 2, and we're using SAR interferometry, or InSAR, to measure the ground surface subsidence due to groundwater extraction. This session, or part of the series, we want to give some basic understanding of the physics of SAR interferometry. I want to describe how the SAR, or synthetic aperture radar interferometric phase, tells us about what the land surface is doing, and the subsidence, measurement of subsidence. And we're going to be doing a demonstration of data processing to analyze a time series of these SAR interferometry measurements to measure how the ground surface is changing over time. And we give a brief introduction to how to understand how the information from SAR interferometric images and the time series analysis reveals land subsidence due to groundwater extraction, in addition to other processes not covered in this webinar. So to give a more detailed introduction, you should check these previous ARSET tutorials from 2017, the basics of radar, synthetic aperture radar, and SAR processing and data analysis, and the introduction to SAR interferometry. In 2019, there was an interferometric SAR for landslide observations that went into making an interferogram. And last year in 2022, we did an interferometric SAR time series analysis for looking at a landslide. This year, we're going to be using a similar type of time series analysis to do subsidence measurements for over an area of groundwater extraction. So we're going to do a quick review. I'm going to go through this quickly because it's been covered in more detail in those other webinars that you can review on YouTube. The 2017 ARSET training and the 2019 training gives more details on how we actually do SAR interferometry and the SAR interferometry interferogram production. For this tutorial, we're going to be using data that's pre-processed and not going through those preliminary steps. The key thing about SAR interferometry is that we measure the phase of the SAR signal. A lot of the other seminars in this series and elsewhere here in ARSET are using the amplitude, the amount of radar return, but we're actually using the phase of the radar signal, which is a different aspect of SAR that is unique for measuring the surface subsidence. And the phase is a measure of the distance between the radar antenna over here on the shown by this cartoon, and the objects on the ground that reflecting the radar. The key thing is that there's millions of cycles of the radar waves between the satellite and the ground. We don't know the exact number, and that's one of the sources of confusion sometimes in SAR interferometry, is that all of the SAR interferometry measurements are relative. And there's this extra factor that the number of objects within that radar pixel are numerous, and so the actual phase that's returned by a single radar image are relatively random. But if the objects here in this pixel stay in approximately the same location relative to each other, then we can take a second acquisition and do interferometry or very basically subtraction of the phase to measure this distance between the antenna and the ground. We can't measure the absolute distance, but we can measure how much the distance changed. And so as a basic idea, we have this phase that has a whole bunch of extra constants that are due to that distance in phase of image 1, and another image with those with the same constants. We can't determine those constants, but if the constants of all the radar propagation stay the same, then we can take the difference and it cancels out all those other constants, and we can therefore measure the ground surface. There's basically two types of SAR interferometry. There's the mapping and topographic determination. That's done by using two radar antennas that are imaging the ground at the same time. The mission that I worked on was the 2000 NASA Shuttle Radar Topography mission, which is recently reprocessed and released in 2018 as NASA DEM. That used the two radar antennas on the space shuttle, but there's also airborne systems and systems such as the German Tandem X that also use this two satellite or two antenna on a single satellite method. And this produces very high resolution topographic maps by using SAR interferometry. And the second type of SAR interferometry is what we call repeat pass interferometry, where we measure the change in the ground surface, not the elevation. In this case, we actually use the elevation data from SRTM or another data source and subtract out the effects of that elevation to measure the displacement of the ground surface. And that's what we're going to be talking about today. So in this case, we're doing what we call differential interferometry. So we have the same radar antenna or a very highly similar one. Basically, several satellite systems now have multiple satellites that are basically identical, and they come back to the same point in space over the Earth and at a different time, and that's repeating the pass of over the Earth. And we take the phase difference, and that tells us the difference in the range, which is shown as rho in this equation. So by taking the interferogram, we can make a map of how much the ground moved in between those two times. And the little picture here is the map of the Hector mine earthquake that happened here in Southern California in 1999. One of the key things to remember is that the sensitivity of SAR interferometry to topography depends on the distance between the two radar antennas, and it depends on the total path length. That means that we're limited in the resolution of measuring topography. It's usually on the order of a meter or tens of meters. SRTM had a sensitivity around 10 meters. But for measuring displacements, it only depends on the radar wavelength. And that's this displacement sensitivity here in the second equation. It only depends on 4 pi over the lambda, which is the radar wavelength. So we're much more sensitive to measuring surface displacements. We can measure it to a small fraction of the radar wavelength. And with radar wavelengths presently operating satellites between 3 centimeters and 24 centimeters, we can measure a few millimeters or a few centimeters of displacements. Another thing that's can cause confusion with starting with the full radar processing is the phase unwrapping step. In this particular demonstration, we're going to be using data that's already been unwrapped. The phase measurement that we do measure with SAR interferometry is actually modulo 2 pi. That means that the phase ends up being wrapped. That interferogram that I showed previously had these color contours. Those are the wrapped fringes. The distance between each one of those contours is half of the radar wavelength. In that case, it was 6 centimeter radar, so each one of those contours was 3 centimeters. But and for most purposes, we want to look at the unwrapped phase, so we have to do an extra processing step to figure out where these jumps are and figure out how many jumps need to be applied to each pixel and get an unwrapped phase. See the other webinars for more explanation about that. The other important thing is what we call the correlation or coherence of the radar. We measure the coherence by doing correlation, which is just looking at how correlated the phase is for pixels that are nearby. The InSAR signals become incoherent due to a number of processes. There's the thermal and processor noise that's introduced in the radar acquisition and in the radar signal processing. That's generally pretty low in most cases. There's the effects of the geometry. If the radar antennas are further apart, then we start to get some different geometry and volumetric scattering. In some cases, if the radar antenna is rotated, that adds to the noise. And then there's this issue that I mentioned at the beginning of whether those objects that are reflecting the radar stay in the same location within the pixel. If there's things moving around within the pixel, then that also causes loss of coherence or decorrelation. And that's one of the key sources. That is the key source of noise for SAR interferometry, and one of the things that we try to estimate in the analysis to have a better idea of what the quality is of the final measurements, because this correlation directly affects the height and displacement accuracy. And if the correlation is very low, then it affects the ability to unwrap the phase correctly. So the other key thing is that the correlation effects are multiplied instead of added. Some of the other effects in SAR interferometry are added together, but the correlation or coherence is multiplied. So that means that if any one of these factors is low, then the total coherence is going to be low. So that's one of the things to remember when looking at interferometric products. And so, as I mentioned earlier, the 3 radar wavelengths that we use for most satellites these days are L-band, that's 24 centimeters, C-band, that's 6 centimeters, and X-band, that's 3 centimeters. In this particular slide over here, we actually have the L-band and X-band acquired at the same time. This was from the Shuttle Imaging Radar mission that flew in 1994. where we had actually all three of these radar wavelengths operated at the same time. And you can see there's quite a lot of difference between the pattern of radar backscatter at the different radar wavelengths. The L band tends to go through the trees and reach the ground, which is better for SAR interferometry if you have any type of vegetation. Whereas the X band tends to bounce off the tops of the trees, and therefore, if the trees are moving around, then the repeat pass interferometry can become incoherent. C band is somewhere in between, and also can also be affected by heavy vegetation. The InSAR mission that's going to be launched next year will have an additional band that's 12 centimeters. It's called S band. And we can take a look and see what the effects of the radar wavelength are on the coherence. This is also from the shuttle imaging radar mission. The shuttle radar mission in 1994 flew twice, in April and October. So we have a 6-month time interval. They managed to steer the space shuttle, into exactly the same location over the Earth so that we could do the SAR interferometry. And on the left of these two figures is the C band, or 5-6 centimeter wavelength. On the right is the L band. And we can see that the coherence is much higher at L band than it is at C band. Over here on the right panel here is a map of the normalized difference vegetation index, a standard measurement of vegetation content, and you can see the high similarity between the vegetation index and the coherence shows that the vegetation is the main cause of the loss of coherence during this 6-month time interval. So that's the background about SAR and SAR interferometry. These are some tables about the satellites that are available for doing SAR interferometry. These are the satellites that have been around for a while, but are largely now not in operation. Most of the early SAR interferometry work was done with the European ERS-1 and ERS-2 between 1992 and 2001. ERS-2 actually lasted for another 10 years, but the gyroscopes weren't working well, and the data from that time interval are more difficult to use. Canadian Space Agency launched RadarSat-1, and it operated from 1995 to 2013. The European Space Agency launched ENVISAT in 2003. It operated until 2010. It actually was operated from October 2010 to April 2012 in a different orbit, which was much less useful for SAR interferometry. The Japanese Space Agency, Aerospace Exploration Agency, JAXA, launched a satellite called ALOS that was operated from 2006 to 2011. All of the ALOS data is now available online from the NASA Alaska Satellite Facility. The German Space Agency launched 2 satellites, TerraSAR-X and TandemX. They fly close to each other to allow that topographic mapping. And those 2 are still actually in operation. Italian Space Agency launched 4 Cosmos SkyMed satellites. One of those has been retired, but they have started operating newer next generation satellites. Canadian Space Agency launched RadarSat-2. That's almost only used for commercial purposes, but it's still in operation. So the newer spacecraft that are present, or the main spacecraft used today, are Copernicus, Sentinel-1, and the JAXA ALOS 2 satellite. Sentinel-1 had 2 satellites launched into the same orbit, Sentinel-1A, Sentinel-1B. Sentinel-1B had a problem in December 2021, so it stopped operations. Sentinel-1A is still operating. Sentinel-1C satellite is ready to replace Sentinel-1B. The satellite is sitting there waiting for a ride to space. And they're not sure when that's going to be, but we hope it's going to be in sometime next year. And of course, I work at NASA, so we are very much looking forward to the NASA ISRO-SAR mission that is planned for launch in early 2020. I'll say more about that in a minute. There are other satellites. The Argentine Space Agency has launched 2 satellites in the SAOCOM-1 series. The amount of data acquired is somewhat limited, and the data access requires getting an arrangement with the Argentine Space Agency. The JAXA is planning to launch ALOS 4. It's also ready for launch, but is waiting for its rocket to be ready to launch. The Italian Cosmos SkyMed Next Generation, they've launched 2 of those. They have 2 more ready to be launched. Canadian Space Agency launched the RadarSat Constellation mission, and it has 3 satellites, but that data is primarily being acquired over Canada and available for Canadians. There's been a number of other satellites. I should point out the Spanish PAUSE satellite, which is basically a clone of TerraSAR-X. It's launched into the same orbit to allow acquisitions and repeat pass interferometry with TerraSAR-X. The new space satellites, Capella, IceEye, and Umbra, those are acquiring data, but they do not have the orbit control to systematically do SAR interferometry, although they have had some cases where they were able to see the satellites were getting close and able to do SAR interferometry on a few examples. So I should say a little bit more about the NASA ISRO SAR mission. NISAR. The NISAR mission is ready for launch. We are hoping it's going to be launched in February, just a few months from now. It's presently in India at the ISRO testing facility. They've connected the radar structure with the main spacecraft bus built by ISRO, and they're testing all the components, and it will be launched on an ISRO rocket from India, we hope in February or March of 2024. As I mentioned earlier, it has 2 radar wavelengths, the L-band radar built by NASA and the S-band radar built by ISRO, and they're both in the same structure, but using a reflector, unlike a lot of the other radar systems, so that we can actually operate the L-band and the S-band simultaneously. And all the science data will be free and open and available from the S-band from ISRO and the L-band from NASA. It's going to have a 240-kilometer wide swath, very similar to the Sentinel-1, but we're using a different technique. It's called sweep SAR, which makes the SAR interferometry much easier to deal with, because there's some issues in the way that the Sentinel-1 satellites operate that add extra complexity, which we believe the ISRO, the NISAR sweep SAR method will avoid and provide better quality data over overall land. That's the other thing about the NISAR mission is that it's designed to have a very high capability of acquiring and downlinking data. So it's going to be turned on over land every time it's over all land. And the other thing is that it's going to be operated in a mode where it's looking to the south, so it's going to have much better coverage of Antarctica than existing previous radar satellites, which generally look to the north, except during temporary changes in their configuration. I can't get into too much detail, but you can see the nisar.jpl.nasa.gov website for a lot more information about NISAR. So now I'm going to talk about using SAR interferometry to measure subsidence from space. On the left here is actually an old image made by Gilles Peltzer here at JPL. When he first started looking for doing SAR interferometry over the Los Angeles area to look for faults, he saw this very strange pattern in the area of near Pomona. And it turns out that there was groundwater extraction here. He made this neat three-dimensional perspective view of the InSAR phase and added in the AAA street map here to show how that ground surface is highly exaggerated. The actual amount of deformation here is 15 centimeters, and it was over 2 years. But it definitely was distorting the ground surface here near the city of Pomona. On the right is an example of subsidence that happened in Arizona. It's a big problem with groundwater extractions in some parts of Arizona, and they had their rates up to 11 centimeters per year, and it causes problems such as these localized sinkholes, fault reactivation, and many other problems. So how does the extraction of groundwater actually cause the ground surface to go down? This is a cartoon from a paper by Devin Galloway and others. We have this sand and gravel in the subsurface, and especially the silt or clay layers in the subsurface has the clay particles are generally sort of flat. So if you take the water out of it, then those particles will rearrange themselves and collapse, and that reduces the volume, which then lowers the land surface. So just some part of that, when these clay layers have the water extracted, then it tends to permanently reduce the volume of water that it can store because the particles have been rearranged. In the more sandy layers, the ground surface can recover because the sand particles do not completely collapse, but the water can refill the spaces. So there's in most cases there's both a seasonal variation of water that causes a uplift and subsidence, and there's a long-term irreversible inelastic subsidence. This is an example of the seasonal deformation over the area of Los Angeles and Santa Ana. There's a big groundwater basin called the Santa Ana Basin to the southeast of Los Angeles. And if we look at in April to September during the dry season interferogram, that shows several centimeters of subsidence. If we look at a February to August, we also see subsidence. But if we look at a September to January interferogram, we see actually uplift. If you look carefully, the colors of these fringes are going the opposite direction. And that means that the ground is gone back up during the rainy season. And if we take a 1-year interferogram from 1996 to 1997, we can see that the ground surface actually reached the same level after 1 year of going down and then back up. So this is the seasonal deformation that's due to those more sandy layers where the groundwater has been recharged. So the paper is here listed on the slide. So most of what I'm going to be talking about, we're going to be talking about today is the Central Valley of California. The Central Valley is this very large valley that runs a large part of the state. The northern part's called the Sacramento Valley. The southern part's called the San Joaquin Valley. Most of the subsidence is happening in the San Joaquin Valley. This is a huge agricultural area, and has estimated agricultural output of about $17 billion a year. It's also about 1/6 of all the irrigated land in the United States. And it's about 1/5 of all the groundwater extraction is from this aquifer system. So as I mentioned, one of the earlier satellites is this ALOS satellite from JAXA. This is a profile showing this on the left here is the wrapped interferogram. Because this is L-band, these color contours are 12 centimeters. So there's a total of about 24 centimeters of subsidence. And on the right here, we're comparing on the red line is the interferometry measurements, and the blue line, the water elevation. And we can see as the water has been extracted over this 4-year interval, generally going down, the land surface is also going down. This is a animation of that groundwater extraction subsidence bowl with a fancy 3D animation showing the subsidence between 2007 and 2011 as both color and highly exaggerated vertical motion. This is exaggerated probably 1 million times. It's a total deformation around 70 centimeters over those 4 years. So this is the subsidence bowl that in the southern San Joaquin Valley that we're going to be looking at in more detail in the demonstration later. So this is another way of comparing the PALSAR measurements in the red line to a GPS station that's in the same area. The green line here is the GPS measurement, which is measured every day. The PALSAR data is acquired roughly once a month, once every 2 months. The PALSAR data only covers between 2007 and 2011. But we also have the water surface elevation measurements. The water surface elevation is with the on the right axis here with the blue colors, and they only measure the water surface elevation once a year or twice a year, so we don't see the details of the seasonal variations, but we can see this sawtooth pattern as the water recovers during the rainy season, but is withdrawn during the summer dry season. There was an overall a rapid decrease between 2007 and 2010. When there was a drought, the water levels recovered somewhat in 2011 and 2012 when there was more rainfall and they extracted less water. This is a major issue in the state of California. They passed a new law in 2015 after seeing some of these extreme amounts of subsidence due to the groundwater extraction. And it's the California Department of Water Resources has been using SAR interferometry since about 2014 to monitor the effects of this groundwater extraction in the Central Valley and other parts of the state. This is another map showing using the Sentinel-1 data and comparing so Sentinel-1 was launched in 2014 or really started acquiring data in 2015. So this is a comparison on the right here between the 2015-2017 Sentinel-1 data and the ALOS-2 from 2007 to 2010. The pattern is very similar, but the subsidence was actually even faster. These are in rates per year during 2015 to 2017 because we had another drought during those years. We've had drought comes and goes in California, and that's one of the reasons that the groundwater extraction rates vary dramatically between one year and the next, depending on how much rainfall there was. This particular year, 2023, we had a huge amount of rainfall in the rainy season, and the groundwater extraction has been almost completely stopped. In fact, they're actually allowing a lot of the water excess water to go back into the ground to recharge some of these aquifers with the huge amount of rain that we had in 2023. These are comparisons between the radar InSAR time series and with more GPS stations, and we can see the very close match between the GPS and the InSAR, both on the overall long-term subsidence and the seasonal cycles. And this is a comparison between the water surface elevation again and at a well that was monitored more frequently. This well was located in the San Joaquin Valley. This was published in Jean-Liu's paper here. The Geosciences 2019. The orange line shows the water surface elevation, and the blue line shows the ground subsidence. And we noticed that the groundwater elevation minimum was in 2015 or late 2015, but the groundwater, the surface elevation change actually had a minimum almost a year later, and that indicates that there's likely a latency or a lag as the deeper groundwater layers can take maybe a year for the water to reach those deeper levels. So even though the water level started recovering in 2016 and 2017, the surface elevation did not recover until much later. And this is also a comparison with precipitation and the precipitation here in the cyan colors at the bottom. We can see this big impulse of higher precipitation in 2017, at the end of that particular drought. On the top here is a measurement of the overall mass of water in the entire area that's measured with the GRACE satellite, gravity satellite. And we can see that the gravity satellite is also showing the same overall removal of water for over the whole basin. So I'm going to give a demonstration now. We're going to be using data from the pre-processed interferograms from the Sentinel-1 satellite. That's been systematically processed by the ARIA project under the Getting Ready for NISAR system. NASA wanted to systematically process some of the Sentinel-1 data over a number of places around the world, so that people could start getting used to using these systematically processed geocoded unwrapped interferograms. And these are now archived at the NASA ASF DAC. The data format of these interferograms is very similar to the unwrapped interferograms that are being processed for NISAR. So we feel it's very important for people to start using these prepare for NISAR, but they're also useful in themselves. And you can find the available pre-processed data by searching at the Alaska Satellite Facility DAC search tool. And you can also download the data through the ARIA tools package. The ARIA tools package is written here, and there's documentation for that at their ARIA tools documentation GitHub. Then once we've downloaded the unwrapped interferograms, we can do a time series analysis to see how the groundwater is subsiding over a time interval. We are doing using this package called MintPy that does the time series analysis. Once we've got the ARIA data set up, we can load it into MintPy and extract how the groundwater is changing over time. And MintPy is also available open source on GitHub, and from this web page, and has an excellent tutorial system with some more of these notebooks. In fact, the notebook I'm going to be using here today is adapted from one of the MintPy notebooks. So I'm going to do a demonstration. This uses the pre-processed data. I'm going to be using a special cloud processing system that you can get an account to use. The Alaska Satellite Facility has a thing called the OpenSAR Lab, and they can provide for non-commercial purposes. You can get a virtual machine that runs in the Amazon cloud to do these calculations. It's all pre-configured, so you can run these notebooks without having to do your own installation. And I'm going to be using that system to run this notebook. See this website for requesting an account on the OpenSAR Lab. Also like to acknowledge Zhang Yunjun, who's one of the main authors of MintPy. He's made a huge amount of effort to build this system for the time series analysis. There's a number of people that have worked at JPL on the ARIA processing, especially Harash Fatahi and David Beckart, and on the time series analysis. and the OpenSAR lab team that built that system to better to make it available and maintain it. And of course, the sponsors at NASA, and a lot of the JPL analysis was actually supported by the California Department of Water Resources. These are the email addresses for me and Zhen Liu. If you want a detailed questions about the use of SAR or InSAR to measure subsidence, Zhen is probably the better person to ask. And the ARSET website. So, thank you for this. That's the concludes the main slide presentation. I'm going to go now to the notebook. So the Jupyter Notebook, we don't have time to go into details about how Jupyter Notebooks work, so I'm just going to go through this. As I mentioned, this is a notebook that was originally developed for the by the MintPy group by Haresh Vatahi and Zhang Yunjun. Also with David Beckart. We showed last year the Los Angeles landslide time series analysis, so we modified it again to do this presentation. I'm going to be using a data set that was pre-processed for the Central Valley of California that was part of the used for the InSAR Solid Earth Team algorithm theoretical basis documents. And that notebook is also available at this website, this GitHub site. And we're going to be using the ARIA S1 Sentinel-1 geocoded unwrapped interferograms pre-processed under the Griffin project. To save time in this demonstration, I'm going to be, we've downloaded the data and ran the ARIA tools processing. I put the steps in here, but we've taken the data already pre-processed and staged it into the Amazon web data set. In the Amazon simple storage system, the S3. So the data is already preloaded for that specific area, and we're going to be using that just to save time during this demonstration. So this first cell of the notebook, I'm going to just clear the previous run here. Just sets up, imports the software and sets up the imports MintPy software. The next one here is we're going to be using a data set that we had previously processed for the Central Valley, track 144. And this next cell says we're going to use the stage data here. So it's already been pre-processed and that we already ran the time series analysis. So it just, these commands here just go to the Amazon S3 bucket and download the pre-processed zip file. Because it's going from one Amazon website to another, it can download very quickly. It's downloaded 2 gigabytes in just a few seconds, or less than a minute. In this case, it's finished preparing the stage data because I've already done. It unzips it. If in this case I already unzipped it, so it's just skip that step. But when you run this notebook, it'll do the unzipping. I've put in here the commands to run the ARIA commands to download the exact same data set. You can modify these commands to download data for any other place where the ARIA data is available, if you want, or to download a different time interval. In this case, we're only downloading the data from the year 2018 to limit the amount of time that we're going to analyze. And there's a total of 90 scenes, 90 interferograms processed by the in the ARIA geocoded unwrapped interferograms for that time interval. These are commented out. That's what the little hash symbol is at the beginning. So they're not actually running anything, but you can uncomment them if you want to see. So we're going to be using the MintPy analysis program, small baseline app.py, and it's if you run just small baseline app -- help, then it prints out a list of how all the parameters work. The next thing you have to do is set up a configuration file. This cell sets up a configuration file that we're going to be using to process this data set. It's just saying where the data is located, and there were some other parameters about how we're going to be doing the processing. These are the steps, again, of how to do the ARIA processing. This is the step to actually load the data into the MintPy dataset. Because I've run this before, it ran very quickly. So when you run the MintPy, it loads all the data into this directory called inputs. There's this over here on the left. Here is the inputs directory. It has these two main files, geometry.geo and the interferogram stack. That's the interferograms loaded into the MintPy format. And if we look, we can run this info.py to see what's in that interferogram directory. There's 86 interferograms, and each interferogram has been has an area of 1,177 pixels by 3,000 pixels. And there's different layers. One of those layers is the coherence. That's the correlation-based coherence, spatial coherence that we mentioned earlier, and the unwrapped phase, plus other information such as the date of each, the two dates that were used to make that acquisition, and the perpendicular baseline between the data sets. There's also a geometry file that has all the information about the azimuth and incidence angle of the two line of sight angles, and the height of the DEM at that location. I'm going to just run all the rest of the cells here. One of the things that for some satellites is important is how the perpendicular baseline is varying with time. With the Sentinel-1 satellites, they keep the perpendicular baselines very short. So basically that we don't have to worry about this, but for other satellites, sometimes this is something we have to worry about. This plot here shows the coherence matrix. That's the coherence for each one of the pairs. It's all here in the blue. It means that all the coherence of all these interferograms is high and they're good quality. And the bottom plot here shows the network of each one of these lines is one of the interferometric pairs connecting the dots where the dates of the acquisitions are. And you can see for this purpose, we're using the interferograms that have short time intervals, not long time intervals, and because this is an agricultural area where the long time intervals tend to lose coherence. One of the other things that's included with the G-coded unwrapped interferograms is something called the connected components mask. That's a mask of how well the phase is connected, and you can see there's an area here to the east that's not well connected. That's the Sierra Nevada mountains, where some of the interferograms in the winter are snow covered, and there's some other places here where some of the interferograms are less connected. One of the things I mentioned earlier is that the interferograms are measured relative to a reference point. So we have to choose a reference point. In this particular case, we allowed the MintPy to choose the reference point. It goes and grabs, looks at the average of that spatial coherence map and finds a place where the coherence is high, and it shows the reference point here at latitude 36.6 degrees, longitude 119.26. So that all the measurements will be relative to this reference point in the rest of the analysis. The next step is to run the actual network inversion. We take those pairs of interferograms and do a least squares inversion to estimate what deformation there is on each point, each date and each point. And then we can take that set of dates and calculate the velocity, which is the average velocity over the course of that year. In this case, we're calculating the velocity over the year of 2018. And then this next plot here, we plot the measured velocity. This black square here is the reference point. So all these velocities are relative to this reference point. In the green colors are the areas where it's basically close to zero a displacement relative to the reference point, and this large blue area is the area of the rapid subsidence due to the groundwater extraction in the San Joaquin Valley. These white areas are the areas where the coherence is low, and we masked those out as being unreliable measurements due to low temporal coherence, which I'll talk about in a minute. And that's the area to the east, when the Sierra Nevada mountains, where there was snow cover. There's also this sort of oblong area to the little bit to the left of and below the center. That's an area of that floods every year, tends to flood every year. It's called the Tulare Lake. That lake actually flooded dramatically this year due to the extreme rainfall in 2023. So the area of low coherence is going to be much larger for 2023 due to that flooding. And we can see that the color scale here is going down to 25 centimeters at the bottom. So there's actually a very large amounts of, and these have been converted to centimeters per year. And so the subsidence rates are very high, up to 30 centimeters per year during 2018. There are other places in the world, especially Mexico City, that are subsiding even faster than this area. I think in some cases, in some years, Mexico City is subsiding at up to 60 centimeters per year. So these rates are very high in many parts of the world, and especially here. So as I mentioned earlier, we have the coherence of each individual interferogram. and midpoint will take the average of the coherence of all the interferograms. And we can see that area of the Tulare Lake has low coherence in a lot of the interferograms, and the area in the high Sierra Nevada mountains that has high low coherence. So the average is low in those two areas. And there's some agricultural fields that also have low coherence, because they get plowed the fields or did some other agricultural modification in a lot of these areas. Some of the agriculture in this area is orchards of almonds and other oranges and other trees, and those tend to be higher coherence because they don't plow the ground surface, and the trees are fairly far apart. So the second, so that's the average spatial coherence. That's the coherence that's measured by the spatial correlation of the phase. We can also measure coherence as in the temporal domain. Because we have a time series now, we can measure how the phase is varying over time. And we can see that there's actually a very similar pattern in the spatial coherence and the temporal coherence. That's a good indication that that they're both measuring the same kind of processes. But the temporal coherence is actually the method that's most accurate for estimating the errors in the velocity. So that's why MintPy estimates the temporal coherence, and it also for the velocity maps like this one back here, this is actually applying a mask based on a threshold applied to the temporal coherence, which you can adjust if you want to use a different threshold. Another way to look at the error analysis is to look at the standard deviation. Because we're doing a linear fit to the velocity with time, there's some standard deviation of the or residuals from that linear fit, and that gives an idea of the likely errors in the estimate of the linear velocity. In this case, the errors can be very high in the area of the Sierra Nevada because of atmospheric effects, but there's also substantial errors in the area of the groundwater subsidence that are due to that seasonal variation that's not included in this linear fit. The other thing you'll notice is that the errors are smaller close to the reference point, and that's because the atmospheric effects are all set to 0 at that reference point, but the atmosphere local atmospheric variations that tend to increase with distance. And so one of the important things to remember is that you should look at this standard deviation of the velocity before interpreting the velocity, because this gives an idea of what the error in the velocity is. So and it's highly dependent on where that reference point is. We can also plot a transect across the subsidence bowl using MintPy. In this case, I've just drawn a line across the part where it's subsiding the fastest, and this line in dashed on the left, and on the right is that section. We can see that the rates here exceed 30 centimeters per year in the part with the fastest subsidence, but it's quite a variable pattern, and that depends on the details of the groundwater extraction and the distribution of those aquifer clay layers or aquitards that are the main cause of the subsidence. So this is a very quick introduction to how we use SAR interferometry to measure groundwater extraction. There's some reference material here on how to use MintPy and ARIA tools, and I'd be glad to answer any questions. Thanks. Oh, well, there's one other thing I wanted to show. We can also take this final output and put it into Google Earth. So this is we took that final velocity map and made a KMZ file that you can then load into Google Earth and display with Google Earth. Thanks.
Thank you for that excellent presentation, Dr. Fielding. And thanks to all participants for the questions that have been coming in. We've been gathering them on a Google Doc, and we will start our Q&A session right now. Dr. Fielding is online, and he'll be answering all questions. Great, so we'll be sharing the Google Doc here shortly. In the meanwhile, we've shared with you the link to the GitHub, and also we realized that in the demo, the text was a little hard to follow on the Jupyter Notebook. We will be fixing that on the video that we will be posting online. Okay, so welcome, Dr. Fielding.
Hello, yes.
So let's get started then with, let's just start working our way down the questions that have been coming in. The first question, is the transmitted wave considered in the decorrelation effects?
Yes, the key thing about these radar satellites is they have a very stable system for transmitting the exact same wave pattern repeatedly over many, many years. So that if that pattern were to change, it could be cause decorrelation, but because these satellites are designed to have this very stable system, that is not a significant source of decorrelation.
Okay, great. Question number 2. With L-band datasets, can I estimate ground deformation caused by soil water potential on a steep slope in the case of landslide and subsidence? How can multi-frequency be an added advantage for this sort of application?
So the L-band SAR is actually can be used to estimate the soil moisture content. And that will be one of the products that's going to be produced by the InSAR mission. They will be producing soil moisture maps globally at 200-meter resolution, and people will be doing similar analysis with the S-band radar wavelength that's more sensitive to the shallow part of the soil. I'm not sure if ISRO is planning to do that systematically. We know that NASA is planning to systematically process all the L-band for soil moisture. That soil moisture is estimated using the radar amplitude images, but the phase of the images, what they we use for InSAR analysis is a different type of analysis of the same data that we can then use to measure the ground displacements due to landslides or groundwater extraction subsidence. The S-band SAR phase can be similarly analyzed for InSAR displacements, and that should give approximately the same result, but the differences between the two radar wavelengths will allow us to better understand the effects of the ionosphere with the effects of soil moisture and vegetation on the InSAR measurements. Those are aspects that are kind of more advanced, but it could be useful in the future.
Great. I will be certainly looking forward to that L-band data from and S-band data from InSAR for these sort of applications. So the next question then is, what climate regions have you noticed that these surface subsidences occur the most from groundwater extraction?
Well, people extract groundwater in places where they don't have enough water from rivers, rain, and snow to use for their needs, such as cities and or agriculture. So the places where there's more groundwater extraction are the places where there's not enough rainfall. So we see the effects of groundwater extraction in places where there's much less precipitation. In places where it rains all the time, typically there's no need to extract water from the ground.
Okay, question number 4. Can Jupyter Notebook be used to conduct InSAR analysis over area in the world? And how much processing time and computational power is required to do this processing on a local machine using Jupyter Notebook?
So this particular demonstration is using the pre-processed interferograms from the ARIA processing of Sentinel-1 geocoded unwrapped interferograms. These interferograms are available from the NASA ASF data archive. You can search for them there. They're processed for some parts of the world, but they're not available everywhere. For other parts of the world, you would need to do your own InSAR, process your own interferograms. Because we're using these pre-processed interferograms, a lot of the processing has already been done. And the analysis, but the total analysis time that it takes to run the notebook will depend on how many scenes you process. For this particular demonstration, I used just 1 year of data. If I had used 6 years of data, it would have taken much longer. The other thing is that these geocoded unwrapped interferograms are going to be one of the standard products from the InSAR mission. So while the Sentinel-1 geocoded unwrapped interferograms from the ARIA project are only available for limited areas, for InSAR mission, they will be available globally.
Okay, question number 5. How do you check for atmospheric interference in the interferogram stack that you use for this small baseline in order to remove those effects if needed?
The time series analysis is one of the key ways to check for atmospheric interference, especially in the troposphere. Tropospheric water vapor is one of the effects that causes apparent InSAR signals. By doing a fit to a year of data, that's one of the ways that I reduce the time series, the atmospheric effects in measuring the velocity of the ground subsidence in this particular demonstration. So by doing a time series fit, that's one of the ways to do it. There's also some more advanced ways of using weather models that have an estimate of what the water, how the water vapor is varying with time. And that is a function that's available in MintPy, but I didn't have time to cover that today.
Okay, so the next question, how long will it take us to be approved for an ASF account?
I don't know the exact time. If 1,000 people suddenly apply today, I think it'll take a while, maybe a week or two. Usually it's just a day or two, but if a lot of people are applying on the same day, it could take much longer.
Yeah, and this is also a question that we can bring up tomorrow. The guest lecturer is Dr. Franz Meyer, and he's the chief scientist for the ASF DAC, and he will probably be able to provide an answer, a timeline for this question. So the next question then, how could you please send the GitHub repo link? And I think this was posted on the chat box, but we can include it here.
Yes, we had the repo link for the MintPy and ARIA tools are in the slides. We haven't yet posted the this notebook. It should be available soon. We will get it into the ASF Open SAR Lab virtual machines come with a set of pre-installed notebooks, and we will get this notebook included in that set after it's been fully tested. There was some issues that we ran into recently that we want to make sure that it's working before we post the final version. The notebook for looking at the landslide in Los Angeles is already in that Open SAR Lab GitHub repository.
Okay, so the next question is question number 8. Till date, I've used two methods to perform InSAR analysis. One is using the Snap tool, following the ESA tutorial. And the second one is PyGMT-SAR open source Python InSAR tool. If I get the final line of sight displacement maps from either of these methods, can I use MintPy to perform visualizations on these final products? Asking because the visualization capabilities of MintPy seem to be pretty good.
Yes, there are ways to load to process a stack of data of interferograms with Snap from the ESA Snap tool. And it is then possible to load those into MintPy. There's information on the MintPy website for how to use Snap interferograms. There's two versions of there's a PyGMT-SAR is a modified version of a software package called GMT-SAR. The original GMT-SAR package is supported by MintPy. I don't know the changes that have been made by the person that's been working on the PyGMT-SAR modified version. So I can't tell you whether the PyGMT-SAR products can be loaded into MintPy. It may that would be something you could ask to the PyGMT-SAR author.
Okay, question number 9. If you had a GPS measurement for a reference point during the time series, how can you include the measured displacements into the processing flow?
That's a good question. The key thing is that all the InSAR measurements are relative. So what we sometimes do is use a GPS station that we know is not moving very much as the reference point. And therefore we tie the InSAR measurements to that reference point. if the GPS measurement is moving rapidly, then you would need to add that GPS motion to the projected into the radar line of sight. If you want to compare that to include that with the InSAR measurements.
All right, so the next question, which is question number 10, how do you compute the deformation rate, centimeters per year, from the time series displacements?
The MintPy package does just does a linear least squares fit to the displacements for all the dates in the time series. You can do a linear fit. You in some case you can also optionally include a seasonal component, which for more advanced analysis. So it's basically doing a linear fit to the time series for every pixel in the image.
Okay, so the next question, number 11, how can we create a data set for SBAS InSAR analysis?
That's we can do that with a number of processing packages. There's the ARIA pre-processed interferograms that we used in this demonstration. You could also process data using the ICE package, ISCE, that's an open source package, or the ESA snap tool. And the ASF also has a on-demand InSAR processing function that you can request them to process data using the ASF Type 3 Gamma is what it's called, processing tool that then also can be loaded into MintPy.
Okay, question number 12. Does MintPy use other techniques besides small baseline?
No, the MintPy package is designed to use the small baseline method. It doesn't do other methods. There is a new package that works with MintPy to do persistent scatterer analysis. That's also available on GitHub. It works with the same files.
Okay, question number 13. Why should I choose a fixed point to determine the velocity? Will the line of sight not be sufficient?
InSAR measurements are always relative. We can't get the absolute displacement, so we have to choose a reference point to do the time series analysis, and by definition the displacement at that point is set to 0. That's just the nature of any kind of InSAR analysis. There's a second part of this question here.
Yeah, actually, I meant to, that's an additional question. So I've
Okay,
included
this
that
next
at the
question,
bottom.
okay.
Yeah. So the next question is number 14. Do you have any experience with using InSAR displacement data as a calibration data set for groundwater models, such as ModFlow, for example?
I have not done this, but other people have used InSAR displacements to better understand the flow of groundwater.
Okay, so moving on then to the next question. Number 15, can this data be used to measure groundwater recharge just as it measures subsidence? Is it as simple as saying positive subsidence values equal groundwater recharge?
Yes, that is true, that when the groundwater is recharged, then the surface moves up. You might call that uplift of the ground surface instead of subsidence. And that is an indication of a recharge of the aquifers.
Nice. Okay, question 16. Is InSAR-based land deformation possible irrespective of area, particularly forest or season?
The Sentinel-1 satellite uses the C-band or 6 centimeter radar wavelength, and that radar will not work well in areas of dense forest for InSAR. That is the main reason why NISAR will be using the longer L-band wavelength to better do InSAR in forested areas. Snow cover will also be a problem in certain areas. Even L-band SAR will not work when the ground is covered with snow.
Okay, so the next question, number 17. In the case of urban areas, what is the effect of construction on the accuracy of the assessment or the measurement?
We can only do the interferometric measurements if the objects on the ground are staying constant when when there's large scale construction, creating new buildings or tearing down old buildings, that will cause a loss of coherence and prevent measurement of the surface displacements. This is actually also a way that we can measure damage caused by earthquakes or hurricanes by looking at the InSAR coherence change that's due to destruction of buildings. We can detect where the buildings have been damaged.
Okay, question 18. Could fluvial geomorphological changes be studied using InSAR?
What fluvial geomorphological changes would generally include erosion or deposition, and those are also effects that are going to change the surface, and therefore we can only see that something has changed. It'll cause a loss of coherence. You could detect where these fluvial changes have occurred, but we can't measure the amount of change except by using the topographic mode of InSAR, such as with TandemX.
Okay, question number 19. I think this question can be interpreted in two ways. So are these data set available to everyone? Or are these data set available all over the world?
Yes. The Sentinel-1 raw data is available for most parts of the world, almost everywhere. And it's free and open. The ARIA Sentinel-1 geocoded unwrapped files are only available for selected areas in where we had funding to process the data. The NISAR geocoded unwrapped interferograms will be available globally and free and open.
Okay, question 20. How do you select the spatial and temporal thresholds for the InSAR processing, and how can it be validated? Or how can you make sure that the SBAS processing was carried out correctly?
Yes. With Sentinel-1, they operate the satellites in a way that we don't worry about the spatial baselines because they're always short. That will also be true for NISAR, and so that's not a problem. The temporal threshold is going to depend on the amount of vegetation in the area where you're working. In an area with moderate vegetation, Sentinel-1 interferograms with intervals of more than usually about 48 days lose coherence. And so then you may need to use only shorter time intervals. So that's the temporal threshold. It depends on the radar wavelength and on the vegetation. For L-band, we hope that the temporal threshold will be closer to a year, except.
Okay. Question number 21. Interesting question here. Is subsidence specifically related to groundwater extraction, or could it be generated from other activities such as oil and gas extraction? And if so, can we use the same methodology that was presented today?
Yes, we could use exactly the same methodology to measure subsidence due to other causes. In fact, I studied subsidence due to oil extraction about 25 years ago in very close to this area in California. There's some very rapidly extracting oil fields. So it's the same methodology.
Great. Okay, so another great question, number 22. Could we expect as an extra feature of MinPy to be able to compute up and down east-west deformation besides only line of sight?
From any given track of data, we only measure one line of sight, but in most places, the satellites acquire data on different tracks that can look at the same ground location at different look directions. And there is a function in MinPy to combine what we call the ascending and descending tracks of data to estimate the up, down, and east-west components. Ascending is where the satellite is moving northward relative to the Earth, and descending is where the satellite is moving southward. So those look in opposite directions and therefore give different line of sight information that can be combined to estimate these two components. But you have to have the two different, so you process the two tracks separately and then combine the resulting line of sight velocities.
Question 23. Do you think that we can correlate InSAR line of sight displacement results with GRACE groundwater trend data? Would this be meaningful?
Yes, people have thought about ways to do this. The big difference is the spatial scale. GRACE measures the groundwater change, mass change at about a 400-kilometer spatial scale, whereas InSAR is measuring change on a 100-meter spatial scale. So that's a factor of 1,000 difference in spatial scale. So it would require some thought how you can combine those effectively.
Okay, and going back to the previous question about using this method to look at subsidence due to oil extraction, someone wrote on the chat box that they would be very grateful if you could share some links to studies related to this. So that's perhaps something that can be included in this document when we post it.
Sure, I can link to my paper from 1998.
Oh, wow. Wonderful. Okay. So let's move on then to the next question, number 24. Can SAR track and monitor groundwater content in an alluvial aquifer that surrounds a river as stream flow increases and decreases?
You might be able to measure variations in groundwater due to river flow, but I suspect the amplitude of those variations are much smaller than what we can measure with InSAR.
Okay, question number 25, a very interesting question here. What are some of the potential applications of these techniques that were discussed today for interplanetary missions? How are the current missions that are being planned for interplanetary missions using this sort of technique?
The NASA Veritas mission is planning to use SAR interferometry to measure displacements on Venus. So it's an approved mission. It's planning to go to Venus.
All right, number 26, question 26. What will be the difference in ground deformation derived from L-band and X-band? And which one is more suitable for geohazards?
The ground displacements should be the same, but the difference will be primarily in the coherence of the measurements. If it's a unvegetated area or urbanized area where there's little change in little vegetation, they should give similar results. But in vegetated areas, especially forest, X-band will be completely incoherent and therefore not be able to make any InSAR measurements.
Okay, question 27. Is it possible to monitor urban water pollution with SAR data?
Water pollution. The SAR data does not penetrate into water, so we can't measure anything about the water quality.
Question 28. Have there been significant developments in land subsidence prediction? And if possible, could you share some resources for further reference?
The California Department of Water Resources has been using InSAR for several years now to monitor groundwater extraction throughout the state of California. The area of extreme subsidence that I showed in the demonstration is one of the areas that they are selected for the first effort to control groundwater extraction in the state of California under a new groundwater control law that takes effect in the next few years.
Okay, and then the final question, have there been developments made toward real-time InSAR analysis? And if so, can you share any references?
Not sure what they're referring to with real-time InSAR. The processing of SAR images takes some amount of time. So there's always going to be some amount of delay. With the present satellite systems, it usually takes several hours for the data to be actually be sent down to the ground. So we don't usually talk about real time, but we talk about near real time products for SAR and InSAR analysis.
Okay. Oh, and then I guess we received another question here. Number 30. How is measured subsidence affected by crop phenology? If we're measuring an area where the crop is growing, also, what is the spatial resolution we're looking at in this product? Is it 10 meters?
So the growth of vegetation, crops, usually causes a loss of coherence. So you might be see the amount of coherence loss as a measurement of the amount of crop height change. So generally, that's why we use the longer radar wavelengths, so they're less sensitive to changes in the trees to get to InSAR measurements. What is the spatial resolution? The ARIA Sentinel-1 geocoded unwrapped interferograms are processed at 90-meter resolution. It's possible to get higher resolution with, but that's the standard products are at 90 meters spacing. You could get down to about 30 meters with Sentinel-1. Other satellites might be smaller, higher resolution, especially the X-band satellites.
Okay, and we have yet another question here. It is now related to a DEM. So how accurate would a DEM be that is derived using InSAR?
The accuracy of InSAR DEM depends on the distance between the two radar antennas and the resolution of the SAR images used. So for SRTM, the accuracy was on about 10 meters elevation. For the Tandem X mission, it's better, probably around 3 meters.
All right, and
it's the InSAR height accuracy. is 10 meters. There's airborne radar systems that have higher accuracy.
Okay, we have another question coming in. It's not on the Google Doc here yet, but the question is, do you have experience using InSAR displacement data as a calibration data set for groundwater models such as ModFlow?
Didn't we answer that before?
Did we? Okay. I thought it might be familiar. Okay, so here's another one. Crops, to map crop water consumption, is it possible to do this with SAR? And what would be the best method?
Crop water consumption. The InSAR is really only sensitive to the ground surface. The use of water by the crops would be more from the soil moisture measurements that are not using InSAR, but the SAR amplitude images.
Okay, great. So I think that's it now in terms of the questions that have come in. So that will mark then the end of this Q&A session. I would like to thank our speaker once again, Dr. Eric Fielding, for this great presentation demonstration, for really introducing this topic on looking at subsidence from groundwater extraction with InSAR for the first time in an ARSET training. I'd like to remind everyone that the presentation, the recording, and the transcript for this Q&A will be posted online in the training page for this webinar series. The next session is tomorrow. Tomorrow, November 1st, Wednesday, and we will have Dr. Franz Meyer from the Alaska Satellite Facility and also University of Alaska Fairbanks. He will be talking about detecting and monitoring floods with SAR. I'd like to also remind you that there will be a homework associated with this webinar series, and that will be made available tomorrow. So it will be open up tomorrow, and you will have until November 17 to send in your homework. And for those that have attended live and that complete the homework by the due date, those people will receive a certificate of completion. So before I close, I would like to thank the ARSET team for making this possible: Brock Blevins, Selwyn Hudson-Odoi, Natasha Johnson-Griffin, Sarah Kutshaw, Jonathan O'Brien, Amita Mehta, Sean McCartney. And I would like to thank all of the participants for your enthusiasm, for all the great questions coming in, and for your overall interest in SAR. So before closing, Dr. Fielding, would you like to say any final words?
Well, thanks to people for joining the live session here, and we hope that people will learn and apply this to their own areas, and we're looking forward to NISAR mission launch next year.
Absolutely, very much looking forward to that. So with that, we end today's session. Wishing everyone a great day, and please tune in tomorrow for the final session. Thank you.
Thank you.